Hi friends, you may know that all electrical things such as bulbs, fans, machines, they have a certain resistance. For example, when electric current passes through the filament of a bulb, the filament opposes the flow of current. Now, does this wire have a resistance? The answer is yes. Even though the wire is a good conductor of electricity, it has a resistance. The resistance is usually small. In this video, we'll be looking at what are the factors that affect the resistance of a conductor, like this wire, and the concept of resistivity. I'm going to make the concepts really easy for you. First, let's revise the concept of resistance. When electric current flows through a conductor, like a wire, the wire opposes the flow of current through it. This property is called resistance. Now, this seems strange. Why would any conductor want to oppose the flow of current in it? To understand, we'll need to look deeper into the wire. A wire is made of a metal like copper. The outermost electrons in each copper atom are loosely bound to the nucleus. These outermost or valence electrons are free to move around in the wire. That's why they are called free electrons. Now, when voltage, or what we call as potential difference, is applied across the ends of the wire, these free electrons move in a specific direction. This flow of electrons in a certain direction is called electric current. The wire, which is made up of copper atoms, has a huge number of free electrons. That's why the wire is a good conductor of electricity. So the movement of free electrons is the electric current. But what is the cause of resistance in the wire? Remember, the wire is not hollow. It is made up of solid copper metal. The wire is made up of copper atoms. Since the copper atoms lose their free electrons, they are actually copper ions. So the wire contains two things: free electrons and copper ions. Now let's visualize resistance in an interesting way. Let's imagine the tiny free electrons to be bees and the copper ions to be people. The wire can be visualized as a corridor full of people. Now the bees have to fly from one end to the other end of the corridor. And when they are flying, they'll hit against the people. And the bees will need to find gaps to reach the other end. So the people are like resistance to the flow of bees. Similarly, the copper ions are resisting the flow of electrons. That's why the cause of resistance is the material of the wire, the copper ions present in the wire. How can we calculate the resistance of a conductor like a wire? We can use Ohm's law. Remember Ohm's law? Current is directly proportional to the potential difference applied across the conductor. Now, according to Ohm's law, resistance is the ratio of electric potential applied on the conductor divided by the current flowing in the conductor. So, R is equal to V by I. Now, what is the unit of resistance? That's right, Ohm. It's denoted by this omega symbol. And it's easy to remember. Ohm's law and the unit of resistance is Ohm. Now, one important point to note is that all materials don't follow Ohm's law. The materials that follow Ohm's law are known as ohmic conductors. Conductors made of metals are usually ohmic conductors. They obey Ohm's law. Now let's look at the factors affecting the resistance of a conductor like a wire. We are going to look at these four factors. How does the resistance of a conductor change if you change the length of the conductor, or if you change the thickness of the conductor, that is the area of cross-section of the wire, or if you change the material of the conductor, and if you change the temperature of the conductor? Then how does the resistance of the conductor change? Let's start with the first factor, the length of the conductor. we can imagine this wire to be a thin cylinder like this. Now let's say the wire has a resistance of 1 ohm. Now if we use a wire that is double the length, how does the resistance change? Let's use our bees and people in the corridor analogy to see what we can expect here. If the length of the wire is doubled, this means that the length of the corridor is doubled. And remember, it's completely filled with people. Now since the bees have to travel double the distance now to reach the end, the resistance will be more. In fact, we expect the resistance to be doubled. Remember, bees were the electrons and the people in the corridor were the copper ions in the wire. So the resistance of the wire should be 2 ohms, doubled when the length of the conductor is doubled. And this is exactly what the scientists found when they did their experiments. When they doubled the length of the wire, the resistance of the wire was doubled. Now if the length of the wire is tripled, then the resistance will be, that's right, tripled. And what do you think happens when the length of the wire is half? So it's half the length. Correct. The resistance of the wire will be halved. Now our bees need to go through a corridor that is half the length to reach the end. So the resistance will be halved. So mathematically we can say R is directly proportional to L. That is, the resistance of the conductor R is directly proportional to the length of the conductor L. Now let's look at the second factor, the thickness of the wire. That is the area of cross-section of the wire. Now what does this term mean? Area of cross-section. For example, if you look at a pencil, what is the area of cross-section of this pencil? If we imagine the wire to be a cylinder like this, then the area of cross-section is going to be the area of this circle. Now let's say the area of cross-section of the wire is increased. What do you think? Will the resistance of the wire increase, decrease, or remain the same? That's right, the resistance will decrease. Now let's see why. In our bee and people example, if the corridor is made wider, how do you think the resistance will change? When the area of cross-section of the corridor is increased, that is, the corridor is made wider, it can fit more people in it. The number of people have increased. But note that the number of gaps between the people has also increased. So the bees will have more gaps to go through and they'll find it easier to reach the end of the wider corridor. Similarly, the free electrons will find it easier to go through a thicker wire with a larger area of cross-section compared to a thinner wire. Because there's more space, there'll be lesser collisions between the free electrons and the copper ions in the wire. So the resistance of the wire will decrease when the area of cross-section is increased. The scientists did experiments and saw that when the area of cross-section of the wire is doubled, the resistance becomes half. Similarly, if the area is tripled, then the resistance becomes 1/3. Now what do you think will happen when the area of cross-section of the wire is halved? That's right, the resistance of the wire gets doubled. Since the area of cross-section is halved, the resistance will increase and it will become double. And based on these experiments, the scientists concluded that the resistance of the wire is inversely proportional to the area of cross-section of the wire. R is inversely proportional to A, where R is the resistance of the wire and A is the area of cross-section of the wire. Next, let's look at how the resistance of the wire depends on the nature of material of the wire. So instead of a copper wire, if we have an iron wire of the same length and the same area of cross-section, then the resistance of the iron wire will be about 6 times more than the copper wire. And if we use nichrome material to make the wire, Do you know that nichrome is an alloy of nickel, chromium, manganese and iron? Then the nichrome wire of the same length and the same area of cross section will have a resistance about 60 times more than the copper wire. So as you can see, the resistance of the wire depends on the nature of material of the wire. Now let's look at the last factor that affects the resistance of the wire. It's the temperature of the wire. Now what do you think happens when the temperature of the wire is increased? Again, let's use our bee and people analogy. Now when the temperature is increased, the material gets heated up. So the people in the corridor gain more kinetic energy. You can imagine the people jumping and moving with more energy in their positions. Now this makes it harder for the bees to reach the end, since there will be more collisions with the people. Similarly, when the temperature of the wire is increased, the copper ions gain more kinetic energy and they start vibrating more about their main positions. So there are more collisions between the free electrons and the copper ions in the wire. The free electrons find it more difficult to flow through the wire. And so the resistance of the wire increases with increase in temperature. Now using experiments, it has been found that the resistance of pure metals increases when the temperature of the wire is increased, and the resistance decreases when the temperature of the wire is decreased. But the resistance of alloys such as manganese, constantan and nichrome is almost unaffected by the temperature. As we saw, the resistance of a conductor depends on these four factors: the length of the wire, the area of cross section, the material and temperature of the wire. Now let's see how we can combine these factors to get a formula for the resistance of the wire. We know that resistance is directly proportional to the length of the wire, and resistance is inversely proportional to the area of cross section. Now if we combine these two factors, we get R is directly proportional to L by A. Now if we want to convert this directly proportional relation into an equation, we need to use a constant of proportionality. So we get R equal to rho L by A. And the constant rho looks like a P and is called the resistivity of the material. Resistivity is also called specific resistance, and resistivity depends on the material and the temperature of the wire. It does not depend on length, area of cross section or the shape of the wire. Now we can use this formula that we have, R equal to rho L by A, to define resistivity. Let's take the length of the wire as 1 meter and the area of cross section of the wire as 1 meter square. So if we substitute these values into the equation, we get R equal to rho. So resistivity is numerically equal to the resistance of a wire that is 1 meter long and has an area of cross section of 1 meter square. What is the unit of resistivity? You don't need to remember it. Again, we can use this formula R equal to rho L by A to easily work out the units. Let's first bring resistivity rho to the left hand side. So we get rho equal to RA by L. Now let's substitute the units in the equation. The unit of resistance R is ohm. The unit of area of cross section A is meter square and length is meter. So we get the unit of resistivity as Ohm-meter here. This is the SI unit of resistivity. For example, the resistivity of copper at 20 degrees centigrade is about 1.7 into 10 to the power minus 8 ohm-meter. This value means that if we take a copper wire of length 1 meter and area of cross section 1 meter square, then the wire will have a resistance of 1.7 into 10 to the power minus 8 ohm. the resistivity value of copper is very small, since copper is a good conductor of electricity. But if we change the material, the resistivity value will be different. For example, the resistivity of aluminium is 2.6 into 10 to the power minus 8 ohm-meter. Resistivity of aluminium is higher than copper. Now, if the temperature is increased from, let's say, 20 degrees centigrade to 30 degrees centigrade, then the resistivity value will also increase. So we've learnt that resistivity depends on the material and the temperature of the conductor. Here is the table of resistivity values of different materials at 20 degrees centigrade. Based on this table, which material do you think is the best conductor of electricity? That's right, it's the one on the top, silver. Silver has the lowest resistivity value, so it is the best conductor of electricity. But since silver is very expensive, wires are usually made of copper or aluminium, since they also have low resistivity values. The resistivity of alloys are much higher than pure metals. As you can see in this table, alloys such as manganese, constantan and nichrome have higher resistivity values compared to most metals. Due to the higher resistivity, these alloys are used to make resistance wires, or what we call as resistors. The heating elements, that is the heating coils of appliances such as electric iron, toaster, water heaters and electric kettle are made of alloys such as nichrome. The advantage of using alloys such as nichrome rather than pure metals is that nichrome will produce more heat. For example, if you take a copper coil and a nichrome coil of the same length and cross-section area, since the resistivity of nichrome is higher than copper, the nichrome coil will have higher resistance, and so it will produce more heat, which is exactly what we want for appliances such as the electric iron, toaster, water heater and our kettle. Now, the other advantage is that the nichrome does not undergo oxidation or burn easily even at a higher temperature. So the nichrome wire can be kept red hot without burning or breaking in air. Now let's look at how the resistivity of metals, alloys, semiconductors and insulators changes with increase in temperature. As we had discussed, the resistivity of pure metals increases with increase in temperature. Now, as the temperature increases, the metal ions in the wire, they get more kinetic energy, and so they start vibrating more. The collisions of the free electrons and the metal ions increases. So the resistivity of metals will increase. But the resistivity of alloys such as manganese, constantan and nichrome does not change much with increase in temperature. Semiconductors such as silicon and germanium are an interesting case because the resistivity of semiconductors decreases with the increase of temperature. Semiconductors are used to make solar cells and transistors. The resistivity of insulators, for example glass, diamond and ebonite, is very high and it does not change much with increase in temperature. Now let's see how we can apply the concepts and the formula that we learnt to calculate the resistance of conductors. For our first example, let's say we want to calculate the resistance of a copper wire of length 2 meters and area of cross section 1 centimeter square. To calculate the resistance of the wire, we can use the formula R equal to rho L by A. Here length L is 2 meters. Area A is 1 centimeter square, but we need to convert it into SI units. 1 centimeter equals 1 by 100 meter. So 1 centimeter square will be 1 by 10,000 meter square, which is 10 to the power minus 4 meter square. We can take the value of resistivity of copper from our table. Resistivity rho of copper is 1.7 into 10 to the power minus 8 ohm meter. Since no temperature is given, we are assuming the temperature to be 20 degrees centigrade. Now we can substitute the values in our formula for resistance R equal to rho L by A, and we get R as 3.4 into 10 to the power minus 4 ohm. So the resistance of the copper wire of length 2 meter and area of cross section 1 centimeter square is 3.4 into 10 to the power minus 4 ohms. For our next example, how will the resistance of the wire change if the wire is doubled along its length? So like this. As you can see, when the wire is doubled along the length of the new wire is half. What happens to the area of cross section of this wire? That's right, the area of cross section of the wire will be doubled. So let's see how the resistance of the wire will change. An interesting thing is, no values are given in this question. Let's take the original length of the wire as L, the area of cross section of the wire as A, and the resistance of the original wire as R1. Using the formula, we get R1 equal to rho L by A. When we double the wire, the length becomes L by 2 and the area of cross section will become 2A. We need to find the new resistance of the wire. Let's call it R2. Again, let's use the formula R equal to rho L by A. Substituting the new values in the formula, we will get R2 equal to rho L by 2 by 2A. Simplifying, we get R2 equal to rho L by 4A. To compare the new resistance R2 with the original resistance R1, the simplest thing is to find the ratio. So let's calculate the ratio of R2 is to R1. We will get R2 by R1 equals rho L by 4A divided by rho L by A, and that's equal to 1 by 4. So we get R2 equal to 1/4 of R1. After doubling the wire along its length, the new resistance is 4 times less compared to the original resistance. Now, how do you think the resistivity of the wire will change when the wire is doubled along its length? That's right, there is no change in resistivity, since resistivity only depends on the material and temperature. Resistivity does not depend on length, area of cross section or the shape of the wire. Friends, I hope the concepts are crystal clear to you now. So next time when you're walking in a corridor filled with people, imagine yourself as a free electron and think about the resistance you face. And to revise these concepts, you can go to my website, manochaacademy.com. To make it easy, I'll put the links below. Thanks for watching.